When the Apollo astronauts looked back at Earth from space at the end of the 1960s, they did not see national borders. They did not see cities or wars. They saw a huge blue sphere with oceans covering nearly 71% of the planet's surface. And what always strikes me as strange is that most people look at water every day, but almost never stop to wonder why a small rocky planet located about 150 million kilometers from the sun could retain up to about 1.4 billion cubic kilometers of water for billions of years. According to planetary formation physics, Earth should have been dry like the moon or Mercury. Water is something that disappears very easily when temperatures rise, and early Earth was once so hot that nearly the entire surface was a lava ocean. The strangest thing is not that this planet has life. The strangest thing is that it had oceans right from the beginning. So where did all this water really come from? About 4.6 billion years ago, before there were oceans, before there was a planet, even before the sun, the solar system was just a giant cloud of gas and dust, slowly rotating in cold, dark space. Then gravity began to do what it always does. It pulled everything closer together. As the cloud contracted, the central part became hotter and denser until the pressure and temperature rose high enough for nuclear fusion reactions to ignite. That was when the sun was born. Now here is the interesting part. When the young sun began to shine, the entire inner region of the solar system turned into an incredibly hot place. Temperatures near the young star were so high that water could not exist in the form of ice. It instantly turned into vapor and was blown away everywhere by the solar wind and radiation. You can imagine this like trying to hold a snowflake right in front of the door of a blazing forge. The snowflake has no chance of surviving. Astronomers call the boundary where water ice can begin to exist stubbornly the snow line. In the early solar system, that boundary lay somewhere near the area of the asteroid belt today, about 2.7 times the distance from Earth to the sun. Outside this boundary, water ice and many other frozen compounds could exist. But inside, where Earth was born, there was almost only dry rock and metal. That is why the giant planets like Jupiter and Saturn contain much larger amounts of ice and water-bearing compounds. They formed in colder regions. Earth did not. If you gave all that data to a physicist and asked that person to predict which planet would have oceans, I am almost certain he would not choose Earth. He would say this must be a dry, scorching world with almost no water. And this is where the real paradox begins. That paradox becomes even greater when you look at Earth in the first stage of its history, the period that geologists call the Hadean, beginning about 4.5 billion years ago. That name is not an exaggeration. If you could turn back time and look down at Earth then, you would not see blue oceans, no white clouds, no continents, nothing resembling the modern world. You would see a planet that was almost completely molten. Throughout the first tens of millions of years, countless early celestial bodies continuously slammed into Earth at terrifying speeds. Each impact released so much kinetic energy that the surface rock had no chance to cool. The entire planet was like a giant lava ocean boiling red under the dark space. Surface temperatures in many periods could exceed 1,200 degrees C, enough to vaporize almost every free water molecule as soon as it appeared. This is something important that many people do not realize. Water is not something that exists easily. It is extremely fragile in the face of high temperatures. We are used to seeing oceans as stable and permanent, but in planetary physics, liquid water is actually a very difficult state to maintain. The young sun at that time was also much more violent than today. In the early stage, it continuously unleashed incredibly strong solar winds along with high energy radiation. If Earth tried to create a primitive atmosphere, those radiation streams would blow it away into space multiple times. So you have a planet being heated from both below and above at the same time. Below was heat from impacts and radioactive decay. Above was radiation from a violent young star. Under such conditions, liquid water could almost not exist stably on the planet's surface. But then everything became even crazier. A few tens of millions of years after Earth formed, a primitive planet that we now call Theia began to enter a crossing orbit with Earth. Theia was about the size of Mars. Think about that for a moment. This was not an asteroid. This was an entire planet hurtling toward it at tens of kilometers per second. When the collision happened, the energy released was greater than billions of atomic bombs combined. Nearly the entire Earth's crust melted again. Thousands of billions of tons of hot rock were blasted into space. For many years, scientists did not understand where the moon came from until the giant impact hypothesis was proposed in the 1970s. According to this hypothesis, most of the material ejected from the final collision eventually coalesced into the moon in a relatively short time by astronomical standards. The interesting thing is that the moon rocks brought back by the Apollo astronauts have a chemical composition very similar to Earth's outer layer. And that is one of the strongest pieces of evidence for this idea. But for our story, the most important part is something else. If Earth had retained any water before that collision, most of that water would almost certainly have disappeared into space. Just looking at the energy level of the collision is enough to understand what happened. You cannot keep oceans on a world that has just been completely melted. After the impact, Earth resembled a glowing red sphere surrounded by rock vapor, metal vapor, and swirling hot gas in the darkness. If you were a physicist observing that scene, you would almost certainly conclude that this planet would never have stable oceans. It was too hot, too violent, too chaotic. And that is exactly what makes the whole story so strange. Because billions of years later, the very planet that once resembled hell became the only ocean world we know in the entire solar system. After all that destruction, how did the water still survive? That question leads us to one of the most chaotic periods in the history of the solar system, the time from about 4.1 to 3.8 billion years ago, when the inner planets nearly survived inside a storm of rocks lasting hundreds of millions of years. Scientists call this period the Late Heavy Bombardment. Just hearing that name is enough to make you feel uneasy, but the reality was far more terrifying. After Jupiter and Saturn formed, their enormous gravity began to disrupt the orbits of countless small bodies left over from the solar system's birth period. You can imagine the entire solar system like a dusty room that someone just swept hard with a giant gust of wind. Millions of celestial bodies began to be thrown in every direction. Many of those objects hurtled into the inner region at tens of kilometers per second, and Earth lay right in their path. What always strikes me as strange is that a celestial body does not need to be too large to create a planetary-scale disaster. An object only about 10 kilometers wide, if it hits Earth at cosmic speed, could release energy equivalent to millions of thermonuclear bombs. Now imagine that happening not once but repeating millions of times over hundreds of millions of years. Earth at that time was almost never truly quiet. The sky continuously lit up with giant fireballs streaking through the atmosphere. Each impact created pillars of rock vapor and metal vapor hundreds of kilometers high. Shock waves circled the planet like global earthquakes. There were impacts strong enough to melt entire regions of the crust the size of a country. Some were even capable of boiling any oceans, if oceans existed by then. Some scientists believe that during many stages of this period, Earth's surface was continuously reheated before it had a chance to cool completely. The interesting thing is that Earth today has almost no direct traces left of most of that period, because geological activity has continuously reshaped the surface for billions of years. But the moon is different. The moon has almost no atmosphere, no rain, no oceans, and almost no strong geological activity to erase its history. So it is like a giant museum of the ancient solar system. When the Apollo astronauts brought back moon rocks in the late 1960s and early 1970s, scientists began to realize that the moon's surface was full of scars from enormous collisions. Basins like Imbrium or Oriental, hundreds to more than 1,000 kilometers wide, still lie there to this day. Just the Imbrium Basin alone is more than 4,100 kilometers wide. You have to understand how truly enormous this is. an object powerful enough to create a crater that wide is almost beyond ordinary human imagination. And then the logic starts to become frightening. If the moon, a much smaller body with much weaker gravity, was bombarded so severely, then Earth with stronger gravity must have endured an even greater number of impacts. In other words, our planet once lay in the middle of a near-apocalyptic cosmic rain of rocks, lasting hundreds of millions of years. But right here, a very interesting idea began to emerge in scientists' minds. If countless celestial bodies were continuously slamming into Earth during that period, could they have brought water with them? This is the moment the story begins to change. Up to this point, everything we know argues against the existence of oceans. Earth formed in a region that was too hot. The surface was once a lava ocean. The atmosphere was continuously blown away. A near-apocalyptic giant collision melted nearly the entire planet again. If you look at all that data as a physicist, you would almost conclude that Earth had no chance of retaining water. But now, for the first time, there appeared the possibility that water did not exist here from the beginning. Maybe it arrived later. Maybe millions of ancient celestial bodies slamming into Earth brought not only rock and metal, but also ice, water vapor, and hydrogen-bearing compounds. Maybe the oceans today are actually the result of countless impacts over hundreds of millions of years. And if that is true, then every drop of water on this planet may carry its origin from those wandering bodies in the darkness of deep space, even before Earth truly became a complete world. That idea sounded almost like science fiction at first, but the more scientists researched the early solar system, the more seriously they began to take it. If water could not exist stably on Earth when it first formed, then maybe it was brought from somewhere else. And when you look out to the cold outer regions of the solar system, you begin to see some very interesting candidates flying around the sun for billions of years. We call them comets. Basically, comets are giant ice blocks mixed with rocky dust, frozen gases, and ancient material left over from the time the solar system was just born. Many people often think comets are just beautiful streaks of light in the night sky, but in reality they are more like frozen storage vaults of cosmic history. They formed in the extremely cold regions beyond the snow line, where temperatures were low enough for water, ammonia, and many other compounds to freeze stably for billions of years. That means a comet could contain a huge amount of water locked inside its ancient ice layer. The most famous example is, of course, Halley's Comet. Humans have observed it for thousands of years. Ancient Chinese people recorded it. Babylonians saw it. It appeared in the European sky in 1066, right before the famous Battle of Hastings. And the strange thing is that even though humans had looked at it throughout the length of civilized history, we barely knew what it really was until the 20th century. When modern astronomy developed, scientists began to realize that comets were not just light phenomena in the sky. They were real celestial bodies carrying the primitive material of the solar system. By the 1970s and 1980s, more and more scientists began to think that perhaps Earth's oceans were actually the product of countless ancient comets crashing into this young planet. That idea was extremely appealing. I think partly because it made the story of the oceans almost poetic in a scientific way. Try to imagine it. For hundreds of millions of years, billions of ancient ice blocks from the cold, dark outer regions of the solar system continuously slammed into Earth. Each impact left a little more water, a little more vapor, a little more melted ice. At first, notch. But if that happened long enough and often enough, you begin to have something on a planetary scale. This is where the numbers start to get interesting. The current oceans contain about 1.4 billion cubic kilometers of water. It sounds enormous, but when you spread that amount of water over the entire mass of Earth, it only occupies a very small fraction of the planet. So you do not need every comet impact to retain all of its water. Just a small portion of the water surviving the impact could be enough to create the oceans after hundreds of millions of years of continuous bombardment. And that is why the comet hypothesis became so famous. It explained many things at once. It explained why Earth had water even though it formed in a hot, dry region. It explained why the period of heavy bombardment was important, and most importantly, it turned the oceans into a gift from deep space. This became even more interesting when the European Giotto probe flew past Halley's Comet. This was the first time in human history that we looked closely at a real comet nucleus. I still remember the feeling when the first images were released. Instead of a pure white snowball, as many people imagined, Halley appeared as a giant black rocky block spewing columns of gas and dust into space. But that was exactly what excited the scientists, because it showed that comets did not just contain ice. They were extremely primitive mixtures of water, dust, and ancient material that had barely changed since the solar system first formed. Some astronomers began to call them frozen fossils of the solar system. The more we looked at them, the more reasonable the comet hypothesis seemed. If you had billions of icy bodies continuously slamming into Earth for hundreds of millions of years, it was really not hard to imagine the oceans forming that way. But this is what I always like about science. An idea can sound wonderful, can be very beautiful, even almost perfectly intuitive, but nature does not care what makes humans feel beautiful or logical. In the end, every hypothesis must face the same uncomfortable question. Is it really true? And that was when scientists began to wonder whether all the water on Earth really came from comets or not. That question began to make many scientists look toward another group of celestial bodies that were less famous than comets, but could be far more important to our story. We call them carbonaceous asteroids. If comets are like wandering ice balls in the cold outer regions of the solar system, then carbonaceous asteroids are like ancient material fragments left over from the time the planets were being assembled. The interesting thing is that many asteroids of this type are not dry as people once thought. When scientists cut them open and analyzed their chemical composition, they discovered they contained water-bearing minerals along with many complex organic compounds. This is the part that really made the story fascinating. Unlike comets, most carbonaceous asteroids formed closer to the inner regions of the solar system. That means the chance of them colliding with Earth was much higher. A comet coming from very far away usually only occasionally plunges into the inner region. But asteroids from the asteroid belt are more like millions of rock fragments orbiting the sun right near us. So if you wanted to transport water to Earth through continuous impacts over hundreds of millions of years, these asteroids started to look like extremely plausible candidates. What I like most about science is that sometimes the driest looking thing contains the most interesting answer. Some carbonaceous asteroids contain a few % of their mass as water. It may not sound like much, but you have to remember we're talking about billions of bodies colliding continuously over enormous time. Moreover, the water in these asteroids does not exist as small liquid pockets inside the rock. It is locked at the chemical level. Water molecules or hydrogen and oxygen groups are held within the crystal structure of the minerals. So even when the asteroid looks on the outside like a completely dry black lump of stone, inside it could still be carrying water from the early solar system. That is really strange if you think about it carefully. A small rock flying through space for billions of years could be carrying the components that would later become the oceans of an entire planet. This is where the numbers start to matter. A single asteroid does not carry much water, but a planet is not built from a single impact. It is built from countless impacts stretched across nearly unimaginable time. I like to think about this like a beach. No single grain of sand creates the beach by itself. But when billions of sand grains accumulate over a long time, finally you have an entire coastline stretching for thousands of kilometers. The oceans could have formed in a similar way. Not a single event, not one big disaster creating everything in a single moment, but countless small deliveries stretched across tens of millions of years. Even more interesting is that asteroids still continue to fall to Earth today. Every year, thousands of tons of material from space enter the planet's atmosphere. Most burn up brightly as meteors and disappear, but some fragments survive and fall to the ground. They give us real samples of the ancient solar system. This is almost magical for planetary science. You do not need a time machine to study the early period of the solar system. Sometimes the solar system sends samples to you itself. When chemists analyzed many carbonaceous asteroids, they discovered that the composition of the water locked inside them was very similar to current seawater. That does not mean all oceans definitely came from asteroids, but it made this idea increasingly hard to ignore. And actually, that also made sense according to physical logic. If Earth formed from nearly dry material, but was later bombarded by billions of water-bearing bodies for hundreds of millions of years, eventually you would have a planet beginning to accumulate oceans. The more I think about it, the more I see this is the kind of solution that nature really likes. No single magical moment, no sudden miracle, just physics, time, and small processes repeated on a gigantic scale. But then, just when many scientists began to feel they were getting close to the answer, another even stranger idea started to appear. Maybe the water on Earth did not entirely come from outside. Maybe part of it had been here right from the beginning. That idea at first sounded almost crazy, because if you look at the entire early history of Earth, everything suggests this planet should have been completely dry. But science often becomes most interesting right at the moment when someone starts to doubt what almost everyone believes is obvious. Some geophysicists began to ask whether we were thinking too simply about water. Maybe we imagine water only exists in the form of oceans, rivers, or ice, while nature actually has many much stranger ways to hold water. This is the part where the story begins to shift from astronomy to deep geophysics inside the planet. Even in the hot region near the sun, where water ice could not exist stably, there was still the possibility that some minerals forming with Earth contained groups of hydrogen and oxygen atoms locked inside their chemical structure. That means the material making up Earth may not have been completely dry as we once thought. At first, this idea made many people skeptical, because when you look at Earth in the Hadean period with its lava oceans and temperatures over 1,000 degrees, it is hard to believe any form of water could still exist. But then scientists began to realize something important. Water does not necessarily have to exist in liquid form to survive. It could be held at the molecular level inside minerals. This is what always makes me see nature as playing a game of fooling human intuition. We often think water is either liquid or ice or vapor. But deep inside Earth, physics works in much stranger ways. Some geophysicists began to suspect that Earth's mantle could be holding a huge amount of water inside. Now, when I say water in the mantle, I do not want you to imagine liquid oceans flowing beneath the ground like in adventure novels. Earth's mantle is mostly hot rock under extreme pressure. But at depths of hundreds of kilometers, the pressure is so great that the crystal structure of minerals begins to behave very differently. Molecules containing hydrogen and oxygen can be trapped inside that crystal lattice for extremely long periods. This is almost like a giant sponge on a planetary scale. A sponge may look dry from the outside, but is still holding water inside. Some scientists began to think that Earth's interior could work in a similar way. What made this idea stronger was studies of volcanic rocks. When magma from deep in the mantle erupts to the surface, it often releases water vapor along with many other gases. That shows that at least some water had existed deep below the planet even before volcanic eruptions. So the question began to change. Maybe water was not only brought from outside. Maybe Earth had retained some water right from the moment of formation, then locked it inside the mantle throughout the first hundreds of millions of years. If that is true, then the entire way we think about the origin of the oceans must change completely. The oceans then would not just be gifts from comets or asteroids. Part of them could be something that had come with this planet from the very first day. And what I like most about this idea is that it sounds both logical and strange at the same time, because nature often works like that. It rarely chooses the simplest solution. Instead, it keeps everything in intermediate states that human intuition would never think of. That also explains why the story of water on Earth is so difficult. We are trying to trace the history of something that continuously changes states, continuously moving between rock, vapor, ice, and liquid throughout billions of years. But then that leads to an even bigger question. If part of the water had really been held inside Earth's interior throughout the planet's first period, then how did that water escape to the outside to finally create seas covering the surface of this world? As the planet gradually cooled after hundreds of millions of years of impacts and melting, its outer layer began to harden into a primitive crust. But beneath that crust, Earth's interior was still extremely hot and chaotic. Giant lava oceans continued to move beneath the surface, and the pressure inside the planet began to push gases from deep within the Earth out. This is something very important that people sometimes forget when thinking about the atmosphere. We often imagine the atmosphere as something that always existed around the planet, but in reality, most of Earth's primitive atmosphere may have been created from the interior itself. Water vapor, carbon dioxide, sulfur, nitrogen, and many other gases began to escape through countless volcanic eruptions across the globe. Geologists call this process planetary outgassing. It sounds technical, but in reality it is a very beautiful idea. A hot, rocky planet slowly releasing things trapped inside it into the space above. If you could look at Earth then from a distance, it would look like a giant pressure cooker continuously spewing vapor into the darkness of space. Thousands of volcanoes active at the same time. Cracks in the young crust opening everywhere. Giant columns of hot gas rising tens of kilometers high, then spreading in the thick atmosphere. What always strikes me as strange is that most of the water on the planet's surface today may once have existed as water vapor in that ancient sky. Over millions of years, the amount of water vapor in the atmosphere began to increase nonstop. But this is the very important part. Earth at that time was still not an ocean world. It was still too hot. Many people, when hearing that volcanoes release water vapor, will immediately imagine rain starting to fall and oceans appearing right away. But physics does not work in such an easy way. Try thinking about dropping water onto a red-hot pan. The water droplet just touches the surface and instantly vaporizes and disappears. That is almost exactly what was happening on Earth at that time. Water vapor was continuously being created, but when it tried to condense and fall to the surface, it was vaporized again by the heat from the hot rock. So for a very long time, this planet was covered by a thick atmosphere of water vapor, but still had no stable oceans. This is an image that always amazes me. A world trying to create seas, but not yet cool enough to hold them. That also means the water on Earth at that time was not in the oceans, but suspended in the sky. Scientists believe the atmospheric pressure during this period could have been many times greater than today. Giant clouds of water vapor covering the entire planet. Sunlight penetrating the thick gas layer, creating a hazy red world under a sky almost always full of vapor and volcanic ash. This is the part I like most of the story, because it shows the planet is not a dead stationary object. It is like a system evolving. Earth did not suddenly have oceans in any magical moment. It had to cool very slowly, little by little. Over tens of millions of years, the crust grew thicker, heat gradually escaped into space, and the planet's surface began to approach an extremely important threshold. A threshold where the physics of water was about to change completely. Finally, after hundreds of millions of years since Earth formed, the surface temperature began to drop enough for something that had never happened before to happen. The first water droplets began to have a chance to exist long enough after touching the hot ground of the planet. That moment could be one of the biggest turning points in this planet's history. After tens of millions of years of gradual cooling in the darkness of space, the atmospheric temperature finally began to drop enough for water vapor to no longer exist only as a thick gas layer covering the sky. Water molecules began to condense. The first clouds in Earth's history began to form above a world still full of lava, volcanoes, and glowing red cracks stretching for thousands of kilometers. I always find it strange to think that there was a time in this planet's history when there had never been rain before. Billions of years later, humans consider rain so normal that sometimes they even get annoyed by it. But on early Earth, the first rain was almost a physical revolution. At first, everything happened very chaotically. The first water droplets may have fallen to the surface and immediately vaporized again. Try imagining dropping a few drops of water onto a red-hot pan on the stove. You will see the water just touches the surface, dances around, and turns into vapor instantly. That is almost exactly what happened on Earth at that time. The clouds created rain. Rain fell onto the hot rock, then disappeared back into the atmosphere in just a few seconds. But the important thing is that process began to repeat continuously. Water vapor condensed, rain fell, water evaporated, then condensed again. For millions of years, this planet was like being stuck in a cycle between water vapor and fire. This is the part that always makes me see nature as patient to an unbelievable degree. There was no magical moment when the oceans suddenly appeared overnight. Earth had to cool very slowly, little by little. The surface took an extremely long time for heat from inside to escape into space. Each million years that passed, the planet's crust grew a little thicker. The hot rock regions began to stabilize more. And then finally, at some point more than 4 billion years ago, something that had never happened before happened. A water droplet fell onto Earth's surface and did not instantly disappear anymore. I know it sounds simple, but if you think carefully, that could be one of the most important moments in the planet's history, because as soon as water could exist stably on the surface, the entire future of Earth began to change. A fire planet began to turn into a water planet. At first, perhaps only small bodies of water existed in the depressions of the gradually cooling crust. But then they grew larger, more numerous. The rains lasted longer before evaporating completely. The first streams began to flow across the hot rock. Water vapor continued to condense in the thick sky above. And then that crossed an irreversible threshold. Rain was no longer a temporary phenomenon. It became a stable part of the planet. I always liked this image because it is almost like Earth transitioning to a completely new physical state. In the first hundreds of millions of years, this planet existed in a near-hell state, where hot rock and impacts dominated everything. But now, for the first time in its history, it began to have a water cycle. The first clouds, the first storms, the first flows. That also means Earth's surface began to change in ways that had never happened before. Water began to erode rock. Water vapor began to affect the atmosphere. New chemical reactions appeared everywhere. This planet was no longer just a hot rock in space. It was beginning to become a world with weather. And then the rains continued for long periods. Not for a few days, not for a few years, but possibly for millions of years continuously. Those rains may have been one of the most intense phenomena that ever occurred on this planet. When people hear the phrase rain on early Earth, they often imagine something like a normal thunderstorm today. But in reality, the world at that time was completely different. The entire planet was covered by giant storms that lasted almost nonstop. Water vapor that had accumulated for hundreds of millions of years in the atmosphere now began to continuously condense and pour down onto the scorching surface below. Rain fell onto hot rock, creating enormous white columns of steam that rose back into the sky to continue the cycle once again. For a very long time, Earth was almost like a giant steam engine on a planetary scale. You had water, heat, and pressure working simultaneously across the entire surface of this world. What always strikes me as strange is that all the oceans today may have started from such a seemingly simple process, just water continuously falling onto rock over an extremely long time. But then physics began to change in a way that favored water. Over tens of millions of years, the planet's crust continued to cool further. Those giant hot rock regions gradually stabilized. The first depressed areas on the surface began to have the ability to hold water instead of completely evaporating it. This may have been when the first lakes in Earth's history appeared. At first, they probably did not last long. A new volcanic eruption or a large impact could make them disappear again. But over time, more and more water began to stay on the surface longer than before. Deeper depressions accumulated more water. The first streams began to connect the flooded areas together. And then finally, more than 4 billion years ago, the real oceans began to form. This is something I think many people do not realize. Earth's first ocean probably did not look anything like the seas of today. The water at that time could have been much hotter. Some scientists believe the temperature of the primitive oceans could have been close to boiling in many areas. The sky above was full of water vapor, volcanic ash, and toxic gases. There were no white sand beaches. There were no blue waves under gentle sunlight. This was an extremely violent world. But for the first time in the planet's history, liquid water had begun to dominate the surface. That meant Earth was undergoing an almost complete transformation. In the first hundreds of millions of years, it was a world of fire. Now it began to become a world of water. I always see this moment as almost like a change of physical state on a planetary scale. Just as water transitions from vapor to liquid, Earth was also transitioning from a lava hell to an ocean planet. But even then, this world was still extremely alien compared to the present. Giant black volcanoes rose up in the middle of the primitive ocean, continuously spewing lava and hot gas into the atmosphere. Many areas of the seafloor may have still glowed red beneath the layer of hot water above. Stable continents had almost not yet existed. Most of the planet's surface may have been just sea, with a few small volcanic islands scattered across the dim ocean. The atmosphere at that time had almost no free oxygen. If a modern human appeared there, he would die almost immediately. The air was full of carbon dioxide, sulfur, and hot water vapor. The sky might have had a dull red or orange color under the thick cloud layer. This was not a world for complex life. But right here, on that strange planet, the first conditions for life were gradually appearing. Because once you have stable oceans, everything begins to change. Water began to erode rock and transport minerals across the planet. Surface temperatures became more stable than before, thanks to the enormous mass of water-absorbing heat. New chemical reactions appeared everywhere, especially around hydrothermal vents on the seafloor, where hot water contacted minerals from the Earth's interior. This is the part that always makes me think that water is not just a component of life. It is almost the stage where the entire biological story began. Without oceans, Earth might have remained just a hot rock orbiting the sun, like many other worlds in the solar system. But with oceans, this planet began to have weather, complex chemistry, and finally biology. The strange thing is that all of that depended on water finally winning the battle that lasted hundreds of millions of years between water vapor and fire. The rains were no longer just temporary phenomena. They had completely changed the fate of the planet. And billions of years later, every living thing that has ever existed on Earth, from the first bacteria to modern humans, would all depend on those primitive oceans that had just been born in the darkness of that ancient world. Those first oceans probably looked almost nothing like any sea that modern humans have ever seen. When we think about the ocean, we often imagine blue water under a clear sky, sunlight reflecting on the waves and long coastlines. But Earth, more than 4 billion years ago, was a completely different world. The primitive oceans may not have been blue like today at all. Many scientists believe that seawater during that period contained extremely large amounts of dissolved iron because the planet's crust was continuously eroded by hot water and volcanoes continuously spewed minerals into the sea. That means the water could have had a dark greenish, deep brown, or almost black color under the weak light penetrating the thick, dusty sky. This was not a bright and peaceful planet. The sky at that time might have always been murky with water vapor, volcanic gases, and giant ash clouds. Sunlight passing through the thick atmosphere created a world with colors similar to an endless twilight. The most important thing is that the early atmosphere contained almost no free oxygen. There was no ozone layer. There was no air for humans to breathe. If you stood on the shore of a primitive ocean at that time, what you would smell would not be the familiar smell of sea salt, but a mixture of sulfur gas, hot rock, and thick water vapor. I always find it strange to think that the world we are living in was once so alien that it was almost unrecognizable. Even the first continents at that time were probably still very small. Many geologists believe that most of the planet's surface at that time may have been covered by water, with only a few volcanic rock blocks rising above the sea like giant black islands. That made early Earth possibly more like an ocean planet than at any other time in its history. But this is the really interesting part. The moon at that time was much closer to Earth than it is now. Today, the moon is slowly drifting away from us at about 4 centimeters per year. But if you go back billions of years, it was significantly closer. That meant its gravitational pull on the oceans was much stronger. The tides at that time could have been violently intense to the point of being hard to imagine. Giant masses of water rose and fell continuously around the young planet, pulling strong currents through the hot red volcanic rock regions. You begin to see this entire planet as a giant chemical machine operating on an enormous scale. Hot water, minerals, tides, volcanoes, heat from the Earth's interior, and an atmosphere full of reactive gases interacting with each other continuously. This is the part that always makes me think that life did not appear on a quiet world. It appeared on a planet that was almost chaotic. The interesting thing is that no matter how scary and alien the primitive oceans looked, they still began to stabilize the planet's temperature. Water absorbs and holds heat very well. Once the oceans grew large enough to form, Earth began to change in a much more stable direction than before. Chemical reactions took place continuously in the seawater. Minerals from the Earth's interior dissolved into the ocean. The first cycles between the atmosphere, rock, and water began to appear. And I think this is the most beautiful thing in the entire story. Those oceans that were born from lava, impacts, and steam storms ultimately became the protectors for the future of life. If you looked at Earth then, you would never think this was a world that would give birth to trees, animals, or humans. It was too dark, too hot, too violent. But right in that alien world, for the first time in the planet's history, nature had created an environment stable enough for long enough for chemistry to begin becoming more complex. That means no matter how strange, no matter how toxic and chaotic, those first oceans ultimately still became the cradle of all life that has ever existed on Earth. Those primitive oceans not only changed the shape of the planet, but also began to change its very chemical composition. One of the most interesting questions humans have ever asked is why seawater is salty. It sounds simple because we are so used to the salty taste of the ocean that we almost think it is a natural and obvious characteristic of seawater. But if you really think about it, this question is much a stranger. Pure water is not salty. Rain is not salty. Water vapor is not salty. So where does the salt come from? The answer begins with those ancient rains that lasted for millions of years on early Earth. As rainwater continuously fell onto the planet's surface, it began to dissolve minerals from the rock. This is a very slow chemical process, but extremely powerful if you give it enough time. Water does not just flow over rock. It reacts with rock. It erodes, breaks down, and carries chemical elements along with it. The first streams on Earth began to carry sodium, chlorine, calcium, magnesium, and countless other elements from the planet's crust out to the sea. The ancient rivers at that time were like giant chemical conveyor belts continuously transporting minerals from the continents down to the ocean. The interesting thing is that this process has never stopped. It is still happening right now. Every river in the world today is carrying an extremely small amount of salt to the sea. We just do not notice because it happens too slowly compared to a human lifetime. But if you give physics and chemistry a few 100 million years, those tiny things begin to create results on a planetary scale. This is the part where I always like to use an everyday example because it makes everything much easier to visualize. Imagine you have a bowl of soup being heated continuously. The water in the bowl slowly evaporates into the air, but the salt and dissolved substances stay behind. Over time, the amount of water decreases while the salt becomes more and more concentrated. The ocean works almost the same way. Water continuously evaporates from the sea surface and falls back down as rain. But most of the salt does not go with the water vapor. It stays in the ocean. So over hundreds of millions of years, the amount of salt accumulates more and more. This is what always makes me see the oceans as the chemical memory of the planet. Every drop of seawater today contains traces of ancient rock that was eroded billions of years ago. Some of the sodium in today's seawater may once have been in mountains that disappeared long before the dinosaurs existed. That is truly astonishing if you think about it carefully. The ocean is not just water. It is dissolved geological history. But here is the even more interesting part. Seawater does not become infinitely saltier. If there was only the process of salt accumulation without anything removing it, today's oceans would probably be as concentrated as industrial chemicals. That means Earth also has to have balancing mechanisms. Some salt is locked away in sediments on the seafloor. Some participates in chemical reactions with the ocean crust. Some is pulled back into the Earth's interior through plate tectonics. So the ocean is like a dynamic system, continuously exchanging material with the entire planet. This always makes me think that we often underestimate how alive Earth is. Not alive in the biological sense, but in the sense that it is a physical system continuously moving and recycling itself. The oceans do not stand still. They are changing the planet's chemistry every day throughout billions of years. And in fact, even the salty taste you experience when touching your lips to seawater is the result of a story that lasts nearly as long as Earth's age. It is the product of rain, rock, volcanoes, rivers, time, and planetary physics working together on a scale that the human brain finds very difficult to imagine. I think this is the most beautiful thing about science. It makes even the most familiar things become strange. A person can stand in front of the ocean their whole life without ever thinking much about its salty taste. But when you really look deeper, you realize that even the saltiness of the sea is the result of billions of years of geological history, dissolving in every wave. Most people think the ocean simply lies on Earth's surface like water in a giant bowl. But in reality, the water on this planet has never stood still. It continuously moves, continuously transforms, and even goes deep down into the Earth's interior and returns to the surface in a cycle lasting billions of years. In a sense, Earth is drinking its own ocean. This is where geology begins to feel almost like biology, because this planet is not a dead rock standing still in space. It is like a dynamic system continuously recycling itself. When the oceans formed and Earth's crust gradually stabilized, another phenomenon began to appear: plate tectonics. The planet's crust is not a single solid piece. It is divided into many giant plates that are slowly moving on top of the hot rock deep below. Today, we almost forget that the ground beneath our feet is actually drifting because the movement speed is only a few centimeters per year. But if you give the planet a few 100 million years, those small movements are enough to rearrange the entire world. This is the really strange part. When an oceanic plate slides under another plate in subduction zones, seawater does not just stay on the surface. Part of it is pulled down deep into the planet's mantle. Water is locked in sediments, in minerals, and in the oceanic crust, and then slowly enters Earth's interior. If you think carefully, this almost sounds completely contrary to intuition. We usually think oceans can only lie on the surface. But Earth is actually swallowing part of its ocean down hundreds of kilometers deep. The interesting thing is that the water does not disappear there forever. Under the enormous temperature and pressure in the mantle, the minerals begin to release the trapped water. The water makes the hot rock softer, makes magma easier to form, and then the magma rises back to the surface through volcanic eruptions. So some of the water vapor released from volcanoes today may once have been seawater from tens or hundreds of millions of years ago. I always see this as almost like the planet's circulatory system. The ocean goes down into the earth and returns to the sky in the form of water vapor. Rain falls back into the sea. Then plate tectonics pulls the water down deep once again. This cycle has continued nonstop for nearly all of Earth's history. And this is the part where water begins to no longer look like a minor component. It becomes a core part that makes the planet function the way it does today. Water helps make hot rock softer and more deformable. That is extremely important for the movement of tectonic plates. Without water, Earth's interior could be much harder, and geological activity would be completely different. Some scientists even think that the presence of water itself has helped Earth maintain plate tectonics for an extremely long time. This leads to a very interesting comparison with Venus. When you look at Venus from afar, it looks almost like Earth's twin sister. Nearly the same size, nearly the same mass, similar rock composition. But today Venus is a hot hell with surface temperatures hot enough to melt lead. Almost no liquid oceans exist there anymore. Its thick carbon dioxide atmosphere creates a terrible greenhouse effect that keeps the entire planet continuously heated. What confuses scientists is why two planets so similar end up in two completely different directions. And one of the biggest suspects is water. Earth has oceans. Venus does not. Earth's oceans absorb heat, regulate the climate, and participate in chemical cycles that help keep carbon dioxide levels more stable. Water also supports plate tectonics activity, and plate tectonics in turn helps recycle carbon back into the Earth's interior. So in a sense, water does not just create the seas. It may have helped save Earth from becoming a hot, dead world like Venus. I think this is the part that makes the story of water truly astonishing. At first, we were just trying to understand where the oceans came from. But the deeper you go, the more you realize water is not just something that exists on this planet. It is controlling so many things about how the planet works. It affects climate, geology, chemistry, and finally life itself. But then right at that moment, another question appears. If water is so important, why does it have such strange properties that are almost perfectly suited for life right from the beginning? Water itself is one of the strangest substances in all of nature. We are so used to it that we almost no longer see it as special. You drink it every day, bathe with it, watch rain fall outside the window, and think water is simply water. But if an alien physicist who had never seen life looked at this molecule for the first time, he would probably find it extremely unusual. Basically, water consists of only 2 hydrogen atoms and 1 oxygen atom. It sounds so simple, it is almost boring. But then quantum physics steps in and everything becomes strange. Water molecules attract each other strongly due to a phenomenon called hydrogen bonding. That means each water molecule is like continuously clinging to the molecules around it. This is what makes water behave differently from almost every other familiar liquid. If you look at small molecules similar to water, most would only exist in the gas state under Earth's conditions. But water does not. Thanks to the attraction between molecules, it can exist stably in the liquid state over a very wide temperature range. This sounds technical, but in reality it is almost a physical miracle for life. If water behaved like most other small molecules, the oceans would probably have completely evaporated or frozen long before complex life had a chance to appear. This is the part that always makes me see nature as playing a game with human intuition. We think water is the simplest thing in the world, but in reality, it possesses a whole series of extremely unusual properties. The most famous example is the fact that ice floats on liquid water. It sounds so familiar that most people never think more about it. But if you were a physicist seeing that for the first time, you would find it very strange. Most solids are heavier than their own liquid form. That is why solid metal sinks in molten metal. But water does the opposite. When it freezes, water molecules arrange into a more open crystal structure, taking up more space and making ice lighter than liquid water. So ice floats to the surface. This is extremely important, because if ice sank to the bottom like most other substances, the oceans would freeze from the bottom up. Try thinking about how terrifying that would be. Every winter, the new ice layer would sink to the seafloor instead of floating on the surface. Over time, more and more ice would accumulate at the bottom of the ocean until most of the planet was completely frozen. Many scientists believe that in that case, complex life would probably never appear. But water does not behave in the normal way. It creates a floating ice layer on the sea surface, and that ice layer acts as an insulating blanket that helps liquid water still exist underneath. That means even in icy periods, the oceans can still protect life, and that is only one of the many strange things about water. Water absorbs heat extremely well, meaning the oceans can stabilize the planet's climate by storing and distributing heat around the world. Water is also an unusually strong solvent, allowing chemical molecules to dissolve and react with each other easily. If you start listing all the special properties of water, you will see a very strange pattern. Almost every unusual characteristic of it is extremely useful for life. This is the moment when many people start to feel a little uncomfortable because everything sounds almost too perfect. But I think the interesting thing about science is that it allows you to be amazed without needing to resort to any mysticism. No one designed water to serve life. We exist because nature happened to create a molecule with such special properties. And if the laws of physics were just a little different, the oceans might never have been stable long enough for biology to develop. That also always makes me think that life does not just depend on having water. It depends on water being exactly this strange type of molecule. A molecule that is both simple and almost counterintuitive in everyday terms. Perhaps that is the most beautiful thing about physics. The deeper you look into the most familiar things, the more you realize the universe is not as simple as the human brain once imagined. Sometimes nature creates tricks that go far beyond our intuition, and water may be one of the strangest examples that has ever existed on this planet. Those strange properties of water ultimately lead to one of the biggest questions humans have ever asked. How did life begin? Because as soon as you have stable oceans on a rocky planet, you do not just have water. You have an environment where chemistry begins to become more complex in ways that are almost inevitable. What makes water special is not just that it exists in liquid form. It is also an excellent solvent for chemical reactions. Molecules can dissolve in it, move in it, and collide with each other much more easily. If you want to build a chemical system complex enough to eventually create life, water is almost the perfect environment. The first oceans on Earth did not contain only pure water. They were full of minerals, dissolved metals, and simple organic compounds created from the atmosphere, volcanoes, and asteroids falling from space. That meant the entire planet was like a giant chemistry's laboratory, operating continuously for hundreds of millions of years. Molecules continuously collided, combined, and separated. Most reactions led to nothing special. But when you have an entire planet full of oceans and hundreds of millions of years of time, extremely rare things begin to become almost certain to happen somewhere. This is the part that always makes me see life as seeming both miraculous and completely natural at the same time. There was no magical moment. It was just chemistry becoming increasingly complex in the right environment. One of the most interesting places for this story may lie deep on the seafloor of the primitive ocean. Today we know that at the bottom of the sea there exist giant hydrothermal vents where seawater seeps down into hot rock and erupts back up as superheated streams rich in minerals. Some vents look almost like black chimneys spewing clouds of minerals into the darkness at the ocean floor. What catches scientists' attention is that these places contain enormous amounts of chemical energy, and energy is extremely important for life. Many researchers began to suspect that primitive life may have emerged in those very hot, dark environments. This sounds somewhat counterintuitive because most humans usually associate life with sunlight. But on early Earth, the planet's surface was still extremely violent with strong radiation and continuous impacts. Meanwhile, deep on the seafloor, the ocean water created a giant natural shield. It absorbed heat, stabilized temperature, and protected against many dangerous forms of radiation. Delicate chemical reactions could last longer there. I always like this idea because it makes life begin not under a blue sky, but in the deep darkness under the sea, around the scorching cracks of the young planet. Simple organic molecules may have gradually assembled into more complex structures. Some molecules began to have the ability to self-replicate at an extremely primitive level. And once that happened, the entire history of Earth changed forever. The important thing is that all of this could hardly have happened the way we know it without liquid water. Not only because living things need water to exist, but because the chemistry leading to life itself depended on water from the very beginning. Water helps molecules move and react with each other. It stabilizes the environmental temperature. It transports minerals and energy. So in a very real sense, water does not just support life. It creates the stage where life can begin. And this is the part that always makes this story feel much more personal. Because every living thing on Earth today, from trees and whales to humans, carries traces of the primitive ocean inside their bodies. Your blood contains salt. Your cells operate in a watery environment. Most of your body mass is liquid. In a sense, life has never truly left the ocean. It just took the ocean with it inside its own body. And that leads to an even stranger idea. If water once created life on this planet, then how deep is the connection between water and the human body itself? That idea is truly strange if you think about it carefully. Most people see their body as something completely separate from the ocean. But in a chemical sense, we are still creatures of the sea. About 60% of the human body is water. The brain, blood, muscles, cells, almost every system in your body depends on water to exist. If the amount of water in your body decreases too much in just a few days, life begins to collapse very quickly. This always makes me find it interesting because it means life on land has never truly escaped dependence on the ancient ocean. We just carried the ocean with us in a different form. Your blood is mostly water. Your cells function in a liquid environment. The chemical reactions that create thoughts, memories, and movement in your brain all take place inside water. In a very real sense, each human is a small chemical system floating in liquid, similar to how primitive life once floated in the primitive ocean billions of years ago. What particularly catches biologists' attention is that the ion composition in human blood has many similarities to ancient seawater. Sodium, potassium, calcium, chlorine, all those elements exist in our bodies in ratios that reflect the ancient history of life in the ocean. This is the part that always makes me see biology as almost like chemical archaeology. Your body carries traces of the place where life once began. In a way, life has never forgotten its oceanic origin. It is as if we are still carrying the chemical memory of the ancient sea inside our bodies. This becomes even stranger when you think about the water cycle on the planet. The water in your body today is not new water. Earth has created almost no significant new water for billions of years. That means most of the water existing on the planet today has been continuously cycling through oceans, atmosphere, rivers, living things, and the Earth's interior for nearly all of Earth's history. A water molecule can evaporate from the Pacific Ocean, become a cloud, fall as snow on a mountain, flow into a river, enter the body of a tree, and finally enter your blood. After that, it escapes back into the air through breath or sweat and continues its journey. This is almost like a form of immortality at the molecular level. Hydrogen and oxygen atoms do not care if dinosaurs went extinct or human civilization just appeared. They just keep moving through the planet in endless cycles. That means many water molecules you drink today may once have existed in the body of a dinosaur, in the ancient ocean, or inside clouds that drifted across Earth's sky hundreds of millions of years ago. I always like this idea because it erases the boundary between past and present. We often think history is something that has disappeared, but in reality, part of the planet's physical history is still flowing inside our bodies right now. And if you expand the perspective a little further, everything starts to become much stranger. The hydrogen atoms in your water may have existed since near the time the universe was born. After the Big Bang, hydrogen was the first element to appear in large quantities in the universe. That means part of the water circulating in your blood today has an origin older than Earth, older than the sun, and almost as old as the universe itself. I think this is one of the most beautiful things science has ever revealed. A simple glass of water that even a child would not notice, but inside it contains history stretching from the Big Bang to the primitive oceans of Earth and finally to human life. This also always makes me feel that the ocean is not just the scenery of the planet. It is almost like a giant circulatory system connecting the past with the present. And then the next question almost inevitably appears. If water is that important to Earth and life, is this planet truly special, or is water also existing everywhere else in the solar system? That question begins to expand the story from Earth alone to the entire solar system. And then you realize something very interesting. Water may actually not be rare in the universe at all. In many decades of the 20th century, space probes and telescopes began to detect traces of water everywhere. We see water ice on Mars. We see icy moons around Jupiter and Saturn. We detect water vapor in interstellar clouds where new stars are forming. That means hydrogen and oxygen atoms combining into water seems to be a fairly natural process in the universe. But then you realize something extremely important. Having water and having stable liquid oceans on a planet's surface are two completely different things. This is where Earth starts to look much more special. Look at Mars, for example. Today it is a cold, dry world with a very thin atmosphere. But many geological traces show that billions of years ago, water once flowed on that planet's surface. There are dried up riverbeds, areas that look like ancient lakes, and erosion signs that could only be created by liquid. That means Mars may once have been much warmer and wetter than it is now. But then that planet gradually lost its atmosphere. Its weaker gravity made it unable to hold heat and gases as well as Earth. As the atmosphere thinned, most of the water disappeared. Some froze at the poles, some lies underground, some escaped into space. So today, water on Mars mostly exists as ice or extremely thin vapor in the atmosphere. That makes Mars look like a world preserving the remnants of oceans that died long ago. But then you look in the other direction and see an even more terrifying example. Venus. This is the planet most similar to Earth in size and mass. For many years, some scientists thought Venus might also have had oceans in the past. But if that was ever true, then everything changed in a terrible direction. Because being closer to the sun, temperatures on Venus were a little higher. It does not sound like much, but in planetary climate physics, a little is sometimes the distance between oceans and hell. As temperatures rose, more water evaporated. Water vapor is a strong greenhouse gas that trapped even more heat, causing even more water to evaporate. This was an extremely dangerous, self-reinforcing feedback loop. Eventually, the entire planet fell into a runaway greenhouse effect. Any oceans that once existed began to disappear completely. Today, Venus's surface temperature is hot enough to melt lead. This always makes me see Earth as walking on an extremely thin tightrope. It lies almost at exactly the right distance for water to exist in stable liquid form for billions of years. If Earth were a little closer to the sun, the oceans might have evaporated like on Venus. If a little farther, most of the water might have frozen like on Mars. The strange thing is that the entire history of life depends on that extremely small balance. We often think life is strong because it exists everywhere on Earth. But when looking from a planetary science perspective, you begin to see it as terribly fragile. Just a slight difference in temperature, a slight difference in atmosphere, or a slight difference in the amount of water, and the entire biological history might never have happened. This always makes me feel that the universe is both vast and cold in a very strange way. Water may exist everywhere, but stable liquid water on a planet's surface for billions of years seems much rarer. And if that is true, then complex life may also be rare in a similar way. But then this is the part that really makes me like science. The more we explore, the less certain we are whether all of this is an extremely rare accident or almost an inevitable natural result of the physics of the universe. Because on one hand, Earth looks fragile to the point of being hard to believe. On the other hand, water, organic chemistry, and the elements needed for life seem to appear everywhere in space. So the final question begins to become much bigger. than just the origin of the oceans? Is this whole story an astonishing chain of coincidences? Or does the universe inherently tend to create Earth-like worlds when the right conditions appear? After all that we have just gone through, from comets, asteroids, the planet's mantle to the primitive oceans, scientists still have not completely agreed on the exact origin of all the water on Earth. And honestly, that is actually the most interesting part, because science is not a book where all the answers are already written from beginning. It is like a continuous long investigation, where each new answer opens up even more bigger questions. The oceans may not have come from a single cause. The whole story may be much more complex than choosing one simple solution. Part of the water may have come from carbonaceous asteroids carrying water-bearing minerals from the early solar system. Another part may have come from ice-rich comets slamming into Earth during the period of heavy bombardment. And it is also possible that part of it already existed inside the material that made up the planet from the beginning, then was locked in the mantle for hundreds of millions of years before escaping through volcanoes. What always makes me find nature interesting is that it rarely operates by one single simple cause. The human brain likes neat stories. We want a clear answer, a central cause, one decisive moment. But the universe often does not behave that way. It likes many overlapping processes over extremely long periods of time. That is especially true with planetary history. Earth was not created in one day. The oceans were not either. Everything is the result of billions of years of physics, chemistry, and geology interacting with each other. This is the part I always think people should understand about science. Many people look at science as a set of fixed answers, but in reality its greatest strength lies in its ability to change itself when new data appears. Hypothesis accepted today may be revised or even replaced a few decades later. That is not a failure of science. That is exactly how science works. We build the best model possible from current data, then continue to test whether nature agrees with us or not. If nature says no, we have to change our thinking instead of forcing the universe to fit human intuition. I always like that about physics. It forces humans to be humble. Just think about the story of water on Earth alone. At first, many people thought the oceans had always existed here. Then we realized early Earth was too hot. Then the comet hypothesis became popular. After that, carbonaceous asteroids started to look more reasonable. Next came the idea that the planet's interior might have held water from the beginning. Each time new data appeared, the story changed a little more. And the wonderful thing is that this process itself is real science, not always being right, but continuously getting closer to reality. I think this is why I have never felt disappointed when a hypothesis is revised. On the contrary, that is usually when things start to get more interesting, because the universe tends to be stranger than our initial imagination. We start with a simple question: where did the water on Earth come from? But then that question pulls us through the history of the solar system, planetary formation, the physics of the water molecule, activity deep inside the Earth, and even the origin of life. This is what I always love about science. A deep enough question often connects to almost everything else in the universe. And the more you understand, the more you realize humans have only seen a very small part of the whole story. Perhaps in the future, scientists will discover that most current hypotheses are still missing pieces. Perhaps the real answer will be much stranger. But even now, just the fact that humans can trace back the history of a drop of water for billions of years is already astonishing. A small living species on a rocky planet around an ordinary star can look at the ocean and trace its history back to the time the solar system was just born. That always makes me feel that science does not make the universe lose its beauty. It makes everything much more profound. And then when you look back at this whole story, from the first clouds of gas to the oceans and human life, you begin to wonder about something even bigger. In the entire billions-year history of this planet, where exactly are humans standing? Most of the water on Earth today may have existed for billions of years, much longer than humans, longer than dinosaurs, and even longer than most complex life on this planet. When you drink a glass of water, you are almost certainly not drinking new water. Those water molecules have gone through countless states and countless places in Earth's history. They continuously cycle through clouds, rivers, seas, ice, the Earth's interior, and the bodies of living creatures. This is what always makes me see the water cycle as almost like a form of physical memory of the planet. Water does not just flow through the world. It carries the world's history with it. A water molecule you drink today may once have existed in the primitive ocean when Earth was young. It may once have flown in the hot red atmosphere above primitive volcanoes more than 4 billion years ago. After that, it may have frozen in an ancient glacier, then melted, flowed through rivers, and returned to the sea. The strange thing is that the atoms do not remember what they once belonged to. They just continue moving through the planet's different systems. So the same water molecule may have gone through countless forms of existence before reaching your body today. It may once have been in magma deep underground, then erupted by a volcano into the atmosphere. It may once have drifted in the ocean where the first microorganisms appeared. It may once have been in the blood of a dinosaur, walking through Cretaceous forests. After that, it evaporated into clouds, fell as rain, got locked in ice at the poles, and finally entered a river that modern humans use for drinking water. I think this is one of the most beautiful ideas science has ever revealed. Each person is carrying inside their body a part of the extremely ancient history of the planet. About 60% of your body is water, and most of that water had existed on Earth long before humans appeared. In a very real sense, we do not stand apart from the history of this planet. We are made from the very material that has gone through that entire history. This also always makes me find it strange when humans call water a resource, as if it is just something to consume. Of course, water is an important resource for civilization, but it is much more than that. It is the physical memory of Earth. Every ocean, every river, and every rain is part of a cycle that has operated for nearly all of the planet's history. And what amazes me the most is that this cycle almost does not care about humans. It happened before we existed and will continue long after we disappear. Water molecules will still evaporate from the seas, form clouds, and fall on mountains for millions of years more, no matter what happens to civilization. There is something both humbling and beautiful in that thought. Humans often see themselves as the center of history, but water reminds us that this planet has a history longer than almost anything imaginable. Every drop of water is an ancient traveler that has passed through time longer than every empire, every language, and every civilization. And then when I think about all of that, I always return to the same image, the image of Earth seen from space, a small blue sphere floating in the enormous darkness of the universe. From very far away, the oceans make this planet look almost glowing. The strange thing is that the entire history we just talked about, from ancient comets, primitive volcanoes, rains lasting millions of years to life in humans, all of it is written inside the thin layer of water covering the surface of that world. That image always makes me think that the strangest thing in this whole story is not the oceans themselves. The strangest thing is that a small living species on the planet's surface can look at water and trace its history billions of years into the past. Think about that carefully. The hydrogen atoms in a drop of water you hold in your hand today may have been created from a time very close to when the universe was born. After the Big Bang, when the universe was still hot and dense beyond imagination, hydrogen was the first element to appear in large quantities. That means part of the water in your body is older than Earth, older than the sun, and almost as old as time itself. Just that idea alone is enough to make me feel reality is stranger than any mythological story humans have ever created. But then, what is even more astonishing is that the human brain can discover that. Science allows us to look into a glass of water and not just see clear liquid. It allows us to see the history of comets, of volcanoes, of primitive oceans, and even traces of the early universe inside it. I think this is the most beautiful thing about physics. It turns the most familiar things into doors opening to the history of reality. A person can live their whole life without ever thinking much about water. But when you really look deeper, you begin to realize a glass of water is the result of billions of years of universe history, planetary history, and biology layered on top of each other. That also makes me feel that the more I learn physics, the more I see how small human intuition is before reality. Our brains evolved to throw stones, find food, and survive on the savannah, not to understand planetary formation or the chemistry of the oceans. So almost everything truly profound about the universe goes against everyday intuition. We think water is ordinary, but it is a molecule that is almost bizarre from a physical standpoint. We think the oceans have always existed, but in reality they depend on a fragile chain of conditions stretching over billions of years. We think Earth is stable and obvious, but just a few small changes in parameters, and the entire planetary history could have been completely different. If Earth were a little closer to the sun, water might have evaporated like on Venus. If a little farther, the oceans might have frozen like on Mars. If the collision with Theia had been different, this planet might not have had enough water to maintain seas. If plate tectonics did not work the way it does now, the climate might have become unstable very early. What always strikes me as strange is that the entire human life depends on such a series of fragile balances. We often live as if this world is obvious, but in reality, the existence of the oceans seems like an extremely fragile chain of physical accidents stretched across nearly endless time. And then you begin to feel something very strange. Not a feeling of fear, but a feeling of amazement. Because the more you understand the history of water, the more you realize this planet is not simple or ordinary at all. A world with stable oceans for billions of years may be much rarer than we once thought. A world where chemistry is stable enough for biology to develop may be even rarer. And then on that world, finally a species curious enough appears to ask questions about the origin of the very water in its own body. I think that is the strangest part of the whole story. The universe creates stars, planets, and oceans through blind physics with no clear purpose. But finally, in at least one small place around an ordinary star, matter begins to wonder about its own origin. A part of the ocean begins to think about the ocean. And that always makes me feel that science does not make the world lose its mystery. It makes everything much more profound. Because the more you understand the history of this blue planet, the more you realize how fragile, strange, and astonishing its existence is. That image still always comes back to my mind whenever I think about Earth. A small blue sphere floating in the nearly endless darkness of the universe, with bands of white clouds swirling slowly above the deep oceans. When the Apollo astronauts first saw the planet from that distance at the end of the 1960s, many of them said that experience completely changed the way they viewed humanity. From space, Earth does not look like the center of the universe. It looks fragile, quiet, and almost lonely in the middle of the enormous dark void. But what always strikes me as strange is that most people look at the sea every day, but rarely realize they are looking at the result of a physical history stretching billions of years. The oceans are not something that naturally had to exist. They are the result of a chain of events so fragile it is almost unbelievable. Every wave out there exists because Earth formed at exactly the right distance from the sun. If this planet were a little closer, the temperature might be high enough for most of the water to evaporate like on Venus. If a little farther, the oceans might freeze into a cold, silent world like Mars today. They exist because water molecules have strange properties that are almost unusual in physics. They exist because ancient celestial bodies containing ice and water-bearing minerals once slammed into young Earth billions of years ago. They exist because the Earth's interior is still hot, because volcanoes once released water vapor into the atmosphere, and because plate tectonics continues to recycle water through the planet's interior right up to today. What always amazes me is that Earth actually came close to becoming a dry, barren world many times in its early history. When the planet was still a glowing red lava ocean, water had almost no chance to exist. When Theia collided with Earth with energy greater than billions of atomic bombs combined, Most of the water, if it existed then, was probably blown out into space. When the young sun was more violent than today, its radiation could have stripped away the planet's primitive atmosphere. Just a few physical details being slightly different, and the whole story could have ended very early. But instead of becoming a dry, dead rock in space, Earth managed to keep its oceans for billions of years. And what is even stranger is that this cycle has never truly stopped. Every rain falling to the ground today is still part of the process that began back when the planet was covered by water vapor and primitive volcanoes. Water is still evaporating from the seas, forming clouds and falling on mountains, just as it has done for nearly all of Earth's history. Water molecules that once drifted in the ancient oceans may today be existing in your blood. The rivers are still carrying minerals from the continents out to the sea, just as they did before there were trees or animals. The oceans are still absorbing heat, regulating the climate, and changing the planet's chemistry every day. In a sense, Earth has never truly been finished. It is still a system in continuous motion. And I think that is the most beautiful thing about this whole story. Nature started with rock, fire, impacts, and the cold emptiness of space. No plan, no clear goal, just physics operating according to its laws. But in the end, from all that chaos, the universe created the seas. Then from the seas, it created chemistry complex enough to give rise to life. And finally, in at least one small place around an ordinary star, matter became smart enough to look back at the history of itself. I always see that as the strangest part of science. A part of the ocean begins to think about the ocean. A living species made mostly of water begins to trace back the origin of the very molecules flowing inside its body. That makes me feel that science does not make the world lose its mystery. It makes everything much more profound, because the more you understand about water, the more you realize that a glass of water or a rain shower is not ordinary at all. They are the result of billions of years of universe history, planetary history, and biology layered on top of each other. When you stand in front of the sea and watch the waves crash against the shore, you are not just looking at water. You are looking at traces of ancient comets, of planetary collisions, of primitive volcanoes, and of the first rains that ever fell on Earth more than 4 billion years ago. You are seeing a cycle that has been operating almost from the moment this planet was born until right now. And what amazes me the most is that all of that is still continuing at this very moment. The oceans are still moving, the clouds are still forming, rain is still falling. Water molecules are still passing through living creatures, rocks, glaciers, and the atmosphere just as they have done for nearly all of this world's history. So every time you look out at the ocean, you are not just seeing the scenery of Earth. You are seeing the history of an entire planet that is still in motion. If you want to continue with me exploring the strangest mysteries of the universe, from physics and space to the deep history of this planet itself, please subscribe to the channel and join me in the upcoming stories. And next time when you look out at the sea or hear the sound of rain falling outside the window, remember that you are seeing a part of the ancient history of the universe that is still moving around us.